All right. Good afternoon, everyone. You're welcome to today's edition of the Spring 2023 Seminar Series with Professor Horst being our guest speaker for today. Before I go over to introduce him, I would just want to introduce the graduate student community. This is the leadership team for this academic year, with Roshan and Rachel as the co-chairs, and then we have other members of the leadership team. Honorable Professor Farouk is our mentor, and we usually have regular meetings on Wednesdays by 5:45 p.m. on Zoom, so it's open to anyone who would like to join. It's basically just an interaction where we get to share ideas on how to move the GSC forward, and we invite anyone and everyone to join us. We also have an engaged page from which you can connect with us. You can use either the scan code or the link there to become a member of that and follow what we are doing. And then we also have the LinkedIn account, which you can connect with using the barcode you have here. And lastly, we have a Facebook page as well, where we post news, upcoming events, and some things that are interesting and of importance to graduate students. So you could also use the barcode here to join and connect with us. Then we have a YouTube channel where we basically have videos, like recordings for seminars are uploaded, and then other events that we usually have, where we record and put them on the YouTube channel so that you could go back to follow it if you missed the meeting or you want to get some more information. Then we have this resource for graduate students. It's a team room in the EL building. It's open to graduate students. If you want to have access to it, you can email any of the co-chairs. Their emails are available on the mails that are normally sent out. So you can reach out to them and request for access to the team room, and it will be granted to you. So please, before we get into the discussion, please fill the Google form. We just want to use that to keep a record of those who are in attendance for today. And then would also want to inform graduate students and staff as well of GCOE about our upcoming International Food Festival. It promises to be a lot of fun. We will be having food from different continents, different cultures and nations. And then we'll also be having students from all the different countries, that are part of the graduate students here in GCOE. So we look forward to having your attendance. We promise, we believe it's going to be fun. So please join us. By the way, the link to the Google Sheets is on the chat, I believe. So you can click on the chat and just use that to fill the form. And so without much ado, I'm going to introduce our guest speaker for today. Like I mentioned earlier, he is Professor Hahn, and he will be talking to us today on structural and chemical disorder towards advanced materials. But just a little bit of a biography on him. As you can see on the slide, he's a professor, a visiting professor in the AME and CBME at the University of Oklahoma. But our distinguished professor today also has several experiences that he's had with institutes where he's worked at, both in the US and in Germany. He's had a couple of awards and several scientific publications. He is quite vast in this field of materials science. So we just need to sit back and relax and have him share with us some of the things that he's been working on. So with that, I would invite him, Professor Horst, to take the stage. Thank you.
Okay, thanks for the introduction. Now I need to share the right screen. I don't know. I think this one. Is this now the full screen you see?
Yes, sir.
Okay, so now let me start laser pointer. Anyway, thanks a lot for giving me this opportunity, and I'm glad that you also introduced your organization here, and I see it's very active. It gives a lot of opportunities, and I would congratulate you for such a nice organization, which gives you a very diverse possibility also to interact, with people from different backgrounds. Thanks to Farouk and Janet for making this possible, for inviting me here, and so I'm glad that we can meet, even if it's only online, but maybe in the next few months I will have opportunities to meet you also individually. So today I'm going to present you some of our work, and which was done mostly, and that's why I also have it here on my slide, at the Karlsruhe Institute of Technology, which is located in the city of Karlsruhe in Germany. But because I moved recently in October last year to OU, I have, of course, also the logo here and my affiliation to the two departments or schools, which is shown over here. So let me briefly introduce you to my background, and I'm not going to start from the very beginning. So I'm a material scientist, got my master and PhD in Germany, but then for many years I was also in the US, which started with a 1-year stay, and then it ended up to be almost 8 years. I was at Argonne National Lab at University of Illinois in Urbana-Champaign, and then I had a professorship at Rutgers. But then I decided to move back to Germany. I was at the TU Darmstadt, and then for 18.5 years, I was the executive director of the Institute of Nanotechnology at KIT. I also started a new institute in Ulm for electrochemical energy storage, where I was founding director. Then I spent some more time also in Irvine. And after I retired, and this is a big difference in Germany, it's not as open as in the US. You are retired. There is no way of continuing. And so when I retired, I got this offer to be a distinguished material visiting professor here at OU, and with new roles and so on. But let me describe you briefly, and I understand you are from different backgrounds than material science. I mean, material science is a very interdisciplinary field. So in a way, it also represents some of what the group here is doing in different areas. It involves, of course, synthesizing and processing materials, but then we also are interested, of course, in the structure, and then also in the properties. And this is, of course, already a triangle where it interacts. So it depends how you prepare the material, how you process it, what kind of structure and what kind of properties exist. And material scientists are always interested in establishing the relationships between these different parts. Of course, performance in an industrial environment is also a major issue. And in order to do all of that, we need to characterize, properties, we characterize the structure and so on. And one of the things I already mentioned earlier, of course, in structural characterization is, of course, also electron microscopy. And one of you is also using that type of equipment. Of course, like in other fields of science and engineering, we also have theoretical approaches to understand, and this has become basically in the last few years a fairly new approach, that we would like to predict the behavior of materials, so we can, in the search for new materials or to improve structures, which we can then use in industrial applications, that we can use theory, which is less expensive in a way than doing a lot of experiments. And this more recently also has been a big push to use also artificial intelligence and machine learning in order to accelerate materials development. Yeah, and I think this is a different approach than, for example, Farouk and Janet are using, and we talked about it. And today I would like to show you a few examples of our recent work in advanced materials or advanced nanomaterials, where we have also done a lot of work in the discovery of new materials. Let me briefly introduce the organization where I come from, KIT, which is a merger which happened in 2009 of a university and a national lab. So that would be comparable to the merger of Argonne National Lab with the University of Illinois, to have one institution. So it's a major event which happened in 2009, and the process is still ongoing, because in one case the money comes from the federal government, in the other case from a local state, and that creates a lot of administrative hurdles which are slowly overcome. So we are part of the Helmholtz Association, which might not be so well known as a Max Planck or Fraunhofer in Germany, but it's actually the largest research organization in Germany, and it runs all these national labs, which you see on that long list here. And if you look, it really addresses all the major societal challenges which there are in medicine, in aerospace, in many different areas. And KIT is part of that large organization, which has 42,000 staff members, an annual budget of 5 billion, and a big outcome. It's a paradise for research, I should say, because there's a lot of money available and large equipment is run by it. For example, the DAISY, the German electron synchrotron, where maybe you can also use that. This is the institute where I was director for 18 years and a little bit more. And I don't want to go into it in more detail, just show you some nice pictures of our buildings. It's really a very nice atmosphere which we have over there. And but this might be of interest also to you, because as being member of the Helmholtz Association, we also offer this as a facility. This is called the Karlsruhe Nanomicro Facility. And you see some of the equipment here, which is open also to outside users. You can apply to it, and if your proposal is accepted, you get access to this equipment. But not only you can go there by yourself, but you can also rely on the expertise of the scientists who are running this equipment. So for example, if you would like to use an electron microscope or an atom probe tomography instrument, you can be in contact with the scientists over there and either send your samples or go there and make use of that. So just take a note of this website if you're ever interested and you don't have the equipment available at your hands or here at OU or close by. This is an option which you might want to consider. These are the areas which I would like to cover. So in principle, it's nanomaterials in different varieties. We have worked a lot on metallic classes, so amorphous materials, and we have modified them to the area of nanoclasses, which I would like to introduce to you, and lately also to cluster assembled metallic classes. For about 5 years, we have worked on high entropy materials, and we were among the first ones to introduce high entropy oxides. And our work here, as you can see, has been cited very well, and it has become a major research effort in the last few years when I was there. But we also have established something which I will not introduce today at length, but I would like to at least mention it. You can actually modify materials properties by external fields, for example, electrical fields. And you all know that from field effect transistors. And we have used that concept, and this is interesting, maybe also for people who work with Farouk and Janet, because here it's really a processing issue, how to make out of nanomaterials, how you can make a process which is stable and which yields at the end a printed device. And of course, that would be a lot less expensive than a big machine or a big production line for semiconductor devices. Of course, we don't want to replace the existing technologies, but we would like to add another approach for really inexpensive electronic devices. So here we are really close also to processing technologies and to actually predicting performance. Let me go a little bit into what I meant when I used this title of how we can use composition and defects in order or disorder, how we can use that in order to design materials. So this is one example where we play with a composition. And you know, we do that as material scientists a lot, because no material which we use is just a single element. There's almost no example of that. Even in a semiconductor where we use high purity, we still dope it in order to get the right performance. So we never have a pure element as a material which we are using. And so we can play with a composition. If you build a steel or a magnesium light element for aerospace application, you are typically using alloys. You can push it much further than we have done it traditionally, and you end up with high entropy materials. So typically, if you have a conventional material, you are in one corner of the phase diagram, and you add a few percent of another alloying element or of several elements. But if you go to this new group of high entropy materials, you go towards the center of a complex phase diagram, and you form high entropy metallic alloys or high entropy ceramics. And what you observe is really unexpected, because instead of getting multiple phases, what Gibbs phase rule would predict, you get a homogeneous mixture, a solid solution of 5, 7, 10 elements, as you can see here, and a single phase. So that's surprising, and it opens a whole range of new properties and also new applications. Instead of playing with a composition, material scientists love to play with the structure and the defects. And so that has led to metallic classes. It has led to highly defective nanocrystalline materials. Or what I would like to present to you today is a little bit of an overview on nanoclasses, which are novel amorphous structures, or on cluster assembled materials. So we are playing in a way with defects and with composition, and this is our playground. So this is kind of what I mentioned. A pure metal or pure semiconductor kind of not exists in reality. We typically have metallic alloys, doped semiconductors. We can go in terms of composition, we can go to high entropy materials, which is indicated over here. So we have 5 or more elements in equiatomic composition, or we can also increase, or we go from a crystalline lattice, we go to an amorphous structure. And so we form metallic classes. And all of that, we would like to see how the properties depend. What is the function between the properties and the structure and the composition? And this is a job which we would like to do. So now let's look at, how we go from a perfect to a disordered structure. Let's take, for example, a single crystalline FCC metal, for example, copper. And we can dope it. We put impurity atoms in, or multiple phases, or we put defects in, such as vacancies or dislocations or grain boundaries or precipitates. And then we end up with the alloys which we well know. For example, steel or bronze or brass or different alloys. Or we push it in terms of the doping levels, we push it towards the high entropy materials. If we add grain boundaries to the system, going from a grain size of micron, which is a typical thing which we see in optical microscope of a material, but we can go and make the grains smaller and smaller. And that has, for now more than 30 years, people have looked into nanocrystalline material and their properties and their structure. Or we push it, we're going from crystalline structure, we go to the amorphous state, and we form bulk metallic classes, which you can see here. So this is a disordered structure. It has no crystalline lattice. We only find short range order over a few atomic distances in the material. And you can even modify that, similar to the nanocrystalline concept, and form nano classes, so where the amorphous grains are much smaller and you form interfaces between them. So this is kind of an overview, what I would like to present to you, but I have talked about that, so I can go over that slide very quickly. So what are metallic classes? This is not well established, or it has been discovered only in the late 50s by Paul Dewes, who was a professor at Caltech. And what he did, he rapidly quenched an alloy of gold and silicon, 75% gold and silicon, by splat quenching. So he took a droplet of a liquid metal, which of course is highly mobile atoms, and then he splat quenched it between two plates. And what he obtained was a non-crystalline material. And it was something which was not known at that time, because a class is an amorphous structure was only known from oxide classes, where we have used them for thousands of years. But it was not possible before that experiment to do that also for metallic material. Meanwhile, this technology has been scaled up to industrial levels by using something which is shown here. You have a melt, which is here inductively heated, and then you have a fast-rotating copper water-cooled drum, which onto which you splash the liquid metal, and then you have an extremely high quenching rate. And this is crucial for obtaining in a binary system such amorphous ribbons. And you take the ribbon and you see then you can make kilometers of it, and even up to a width of 1 meter in an industrial level. And if you now go to more complex alloying composition, so you go from binary or ternary to 5, 6, 7 elements in it, you can actually reduce the cooling rate tremendously. You go to a few Kelvin per second, and then of course you can make something which you see here, several centimeters in size, which are then called bulk metallic classes. Okay, and that actually leads to also products. You can make very nice high strength gears, or you can make very small components here in the order of a few micron. You can make golf clubs because they have elastic properties which are not possible in metallic crystalline materials. And then you would like to know the structure. Of course, it's metallic glass. So if you do X-ray diffraction, you don't see sharp peaks anymore, but you see very broad peaks and only 2 of them. You go to the electron microscope, you see something similar. If you go to high resolution electron microscopy, where you can see atomic columns in a crystalline material, here you see a disordered structure and some kind of a theoretical representation of that structure in the insert. So it's a you don't have long-range order like in a crystalline material. And of course, people have thought about it once they have been discovered. And, you know, there was a very famous person, Professor Bernal, and he developed early models of an amorphous structure by ball and spoke model of a liquid. People knew that liquids are, of course, amorphous. They have no structure, but he was thinking about how can the atoms be arranged? And he came up with fascinating ideas. For example, he took steel spheres, macroscopic steel spheres, he put them together, shook it up in a container, and put wax into it. And then he could freeze the whole thing, and he could then take the spheres apart and determine the location. So these are the models which are done on a macroscopic scale. Nowadays, we use computer simulation in order to determine the structure of such complex material. And you see the outcome here, but it really resembles, you know, very much these ball experiments which are, you know, done in the 50s. So it's amazing how these concepts, you know, can be transferred also into today's technologies which we have available. For example, here, this molecular dynamic simulations. You can then look, once you have these atomic arrangements in your computer, you can look what kind of arrangements you find. And here, for different metallic classes, so this would metal, metalloid, or metal classes, you see that the coordination numbers which you find dominating are different for metal and metalloid and metal classes, but you can find, you know, what is called these Caspar polyhedra, which correspond to the different numbers of coordination you have around a central atom. And you can give a certain nomenclature to it, and you see that a metallic class doesn't have a well-defined unit cell like a crystalline material, where we have either FCC, BCC, or other unit cell, but it has a distribution of polyhedra which you assemble together to build this amorphous structure. So locally, you have something which has a short-range order, and that can be different, but there is a certain distribution. So we have short-range order, but that does not translate into a long-range order because these are non-coordinated arrangements. And then you can look into the different materials. I just have here a few examples for different metallic classes which have been studied. So we have a pretty good understanding of the nature of the structure of metallic classes, but still it's not a simple type of thing to, first of all, understand it and also to use it, because you don't have such a nice reference like a crystalline unit cell you have in a crystalline material. So it makes it more complex. You can also look at it in a different way, for example, by using radial distribution function. And radial distribution function you can measure by using neutrons as a particle to do the diffraction, or you can use X-ray diffraction in the synchrotron, or to have also a local information, you can also do it in the electron microscope. And this is here an example where the radial distribution function, so kind of the probability to find another atom or other atoms in a coordination around a central atom. So this is shown here. This would be our central atom. And then here we would have 2 atoms at that distance. And we would have 1 atom at that distance. So this gives you an idea how the radial distribution function looks like. The further you go out in distance from your central atom, then it becomes less and less pronounced in terms of these fluctuations. And you can actually assign distances. So this would be scandium in this binary system. That would be iron, and this would be iron scandium. So you can learn a lot about the local structure of these elements. So now, having talked about a little bit about the structure of these metallic classes, now let's look at a property. If you take plastic deformation of a material and you go to a crystalline metal or an alloy, you have kind of a defect which is a carrier of the plastic deformation. And this defect is called a dislocation, which is a line defect in a crystalline lattice. So it is very well understood how deformation of a crystalline material, single crystal or polycrystalline material, occurs via dislocation motion. And we also know very well how we can influence the dislocation motion and get, for example, higher strengths in the material by doping the material with impurities and preventing dislocations to move. But if you go to an amorphous alloy, you have no lattice and you can have no lattice defect. So the lack of dislocation typically leads to a high strength because the material cannot deform by a dislocation. But it also means once it deforms, it's a catastrophic failure. And you see that over here, shear bands run through the amorphous alloy and it catastrophically fail. We call it the material is brittle. So the shear bands are an interesting part of an amorphous structure because it's where the deformation occurs. But the deformation occurs in a very high speed. It's catastrophic, but you can analyze the shear band after you have seen it, and people have done it. So for example, using electron microscopy technique, like here on the left side, you can see that we have compressive and tensile regions along the shear band. We can also see by analyzing again the shear band in the microscope with another technique, we get density fluctuations. So we have regions where the density is higher, and we have regions where the density is lower. So that's all happens in a very short time of the shear band motion. And what people have also found is that the diffusivity, so the atomic jumps in the shear band, is accelerated by orders of magnitude. So that's interesting because structural changes go in hand with the change of the property of the material. And we have also studied this in more detail, and we have found that within the shear band, by using atom probe tomography, this is a technique where you can find the nature of an element or of an atom in a structure, and also the position to atomic position. And so when you do that, you can see there is a shear band in a small tip, which you can observe over here. And there is a shear band in here where the structure and the composition has changed. And you see there's an enrichment of copper on one side and a depletion, and correspondingly for the zirconium in this binary system. This has also been found for another ternary metallic class as well. Aside from the shear band, it's homogeneous. So we have a homogeneous composition in the shear band. We get a very drastic change of the composition and of many other things. So now I thought, let's look at what a property, in this case, the diffusivity is affected. So we put a little bit of nickel on top of the copper zirconium, and then we looked at the diffusion of the nickel. It only diffuses in the shear band. It doesn't diffuse left and right at that temperature. It only diffuses here. This is orders of magnitude of differences of the diffusivity of the mobility of the nickel atoms in the shear band. You would also observe after this diffusion treatment that this quality of the diffusion profile which we have here of the copper and the zirconium, which occurs during the deformation, this is maintained. There's enough mobility of the atoms to get rid of that kind of fluctuation, but it doesn't want to do that, which indicates that the system wants to be in that state, okay? So there is a state in the metallic class which is different from the rapidly quenched state, which is a favorable structure. And, you know, we have looked at that in other techniques, for example, also with this radial distribution function technique, and we found very much details of that. I want to jump over that for time reasons. So we have indications in the shear bands of metallic classes that we have differences in the atomic structure, which could be a stable new approach. So now I have told you that we can prepare these metallic classes by melt spinning, by rapid quenching. And we have come up with a different approach, which I would like to share with you. And this is a room temperature process where we take nanoparticles, which are amorphous, and we compact them. And in doing that, we do not have the involvement of a high temperature, but everything is done at room temperature, and we form a nanoclass in a way which we have found to be a heterogeneous metallic class, and it has also new properties. There are other techniques which I will go over it, how to prepare that. But this is kind of a simulation which I borrowed from a group at the TU Darmstadt, Professor Alpe, and they have done molecular dynamic simulation of this process of consolidating particles. First of all, they have found that on the surface, you have an enriched enrichment of one element and a depletion of that element on the inside. So once you start to consolidate these particles, you form interfaces, which are shown here in green, where the composition is different, but also the structure and the free volume. And in order to show you this process of the consolidation, I show you this little video, and I think it's almost self-explanatory. So now we compact it, and we get rid of the porosity between the particles, which we have initially. And eventually we have a non-porous, a pore-free material, which you can now analyze because you know all the positions of the atoms in this simulation. And these are, the green is the interfaces, and now this is a cores and so on. So you see, it's an interesting approach to a material synthesis in order to get a different structure. And yes, indeed, the structure is different. And I would like to show you this. And this is what we have done using Mössbauer spectroscopy, which is a technique you might not even have heard about, but that's okay for the present. It looks at the environment of iron 57, which is a naturally occurring isotope of iron. So it gives you information of the environment, both in structure and also in magnetic structure of an iron atom in your material. And if you take, in this case, this is iron scandium material, which we have performed as rapidly quenched by rapid quenching, or the powder, which I use to consolidate later. And you see the spectra, they look identical, because in both cases, the powder and the ribbon was quenched quickly or fast. So once you take that powder and you compact it, what I described earlier, I showed you in that video, you see the spectrum changes dramatically. First of all, there is still a component shown here in blue, which resembles this here. So that's the fraction which is rapidly quenched. But the other one, which is a 6-line spectrum shown here in red, first of all, it indicates that it's magnetic. That's why it has 6 lines. Second of all, it's a phase which was not there before. If you change the particle size, get smaller or bigger, you change the fraction of that red component, which indicates that this is the interfacial region between these amorphous particles. So indeed, we have formed a new metallic glass structure. There is a lot of other experiments which we have done, and it would go beyond here this talk. But what we can say is that we have large density fluctuations between the interfaces and the cores of this. It's all amorphous, but it's clearly a different amorphous structure. And so this makes it interesting to look at, in particular also because we find different properties. For example, I showed you already that it becomes magnetic if we do a different processing, but it also becomes ductile instead of being brittle. So that makes it an interesting new material, maybe in the future. And I show you this also in these videos here of MD simulations. Here you see the catastrophic failure in a homogeneous glass. And here you see how it deforms homogeneously in a nanocrystalline material of the same composition as this side. So it has drastic changes of the properties of the material. And this is an MD simulation, but we can also do that experimentally. I also go over that because it shows detail of the shear band structure in these different materials. So one approach was now, if we have a new amorphous phase, could we also make a material which has 100% of that, which would now be a different amorphous material. And so the idea was, if you start, what I described to you was happening in particles of about 10 nanometer, and then we consolidate it. And then if you would decrease the particle size, the initial particle size, the fraction of interfaces would go up. Yeah, so we would get more and more of this light blue interfacial regime. And the question is really, can we get 100% if we take very small clusters of this material? And up to today, I don't have the answer, but we know we can produce much more of this interfacial regime if we go to a different approach, how to make the clusters. And I jump over this, this describes more of these clusters. I show you just our machine, which we are using now. So instead of compaction of particles, we are now using the energetic impact of cluster ions. So very small, a few hundred atoms, large particles, we call clusters, and they are ionized, they have one charge, and then we can accelerate them onto a substrate. And we can change the impact energy when we build a film out of amorphous cluster ions. And this is just a machine. It's a very sophisticated machine which can create clusters in the source. It can form a beam. It can even size select and then deposit the particles here on the substrate. So if you do that, this is a result, and that has been published already about 3 years ago. But here we produce the clusters and you form a beam, and this just doesn't show the details of it, but we can now deposit the clusters, identical clusters at 50 eV per cluster, 100 eV per cluster, or 500 eV per cluster. And now we studied using a technique called EXAFS, extended X-ray absorption fine structure. We can study the structure, and we see that the structure changes as a function of deposition energy. Moreover, we also see that the magnetic property, the magnetic ordering, is changing, and this is characterized by the Curie temperature, which is the transition temperature between ferromagnetic and paramagnetic behavior. It changes about 60 degrees depending on how we deposit the clusters. And incidentally, if we use 500 eV, that's a very high energy. So imagine you take a snowball and you throw it hard against the floor, it smashes. So it's like rapid quenching. If you let the snowball fall softly, it maintains its structure. And this would be building up an amorphous structure from small particles which maintain the original nature of the particle. And we have, done that here. We show the magnetization curves, and you see clearly the shift of the Curie temperature in this material. We have also simulated that by using MD simulation. This is a PhD thesis of Praneeth Chilla-Kalaputi. He will defend soon his thesis in Germany. So he has looked at the deposition of these clusters and of using molecular dynamic simulation. And then you can again, identify all the atoms where they are and what chemical nature they have. And you can now develop a detailed picture of the local environment of all the atoms. And this helps to understand how the structure of these metallic classes versus the nano classes looks like. And you can get a lot of information out of that. So that was the part I wanted to cover with you on the defects in metallic classes. And now I would like to go over to the part on the chemical disorder and going from, simple oxides, for example, and this is a part we have contributed over the past few years, going from simple oxides to go to complex oxides, which have 5 cations in this case, but in equiatomic composition. And as I mentioned earlier, this way we go to the center of a phase diagram. This has not been explored before. And interestingly enough, you take the different oxides which you put together, they have different structures, but at the end, as we found, we find a rock salt structure. So the other ones kind of are forced into a rock salt structure, even though they don't like it if they are alone. In addition, some of these binary systems are not miscible. They form different phases and so on. But at the end, it's the high entropy which brings the different materials together in a simple rock salt structure. This is symbolized here in this schematic. And you can see this in the XRD or in the XFs or in the APT, here for the structure, and here also for the elemental distribution of the atoms. They are completely statistically distributed in this lattice of the rock salt structure. So we have phase purity in spite of the complexity, and we have a random and homogeneous cation distribution. What is interesting, and this is work by the group of De Maria, a PhD student called Rost, and they have looked at this identical system and published this in 2015. And what they have proven is that this is really entropy stabilized. So if you look at the free energy of a system, it has the enthalpic part, but also a part of the entropy. And the dominant part, if you go into this system, is what is called the configurational entropy. And what you can do now, you go to high temperature, then this part dominates. And this is when you get a single phase. But if you go to lower temperature, of course, this T times delta S term gets smaller, and then eventually this term dominates. And then you have the complex enthalpic interactions of the atoms, and you get other phases. But you can go back and forth, and this proves actually in this system, it's an entropy stabilized configuration we have here. There's a whole variety of different other high entropy oxides. So this is the one I just showed you. We also prepared rare earth high entropy oxide, which have a fluoride structure. We prepared perovskite structure, even up to 10 different cations, which you can see over here. We have 2 sublattices. On one, we have the rare earth, on the other one, the transition metals. And so we have a very complex single phase structure, which has distribution of the element. Meanwhile, the field has been growing tremendously, a lot of interest in it. And that's why also papers are cited quite well. And you see all the different structures which have been prepared. Yeah. But all of that is a nice academic exercise, but it only becomes a field if you find interesting properties. And so people have looked at properties, for example, as lithium-ion conductivity for solid electrolytes in batteries. And this group has found a very high room temperature lithium-ion conductivity in a material which contains up to 30% of lithium in addition to the 5 transition metals. It has also been used in catalysis, and our own work, we have used it as cathodes and anodes for lithium-ion batteries, but also for sodium-ion batteries. So that makes it interesting, in particular, if you have high capacity and good cycling stability, which we have found. And the capacity is substantially better than in this in existing materials. So we have gotten up to 600 milliampere hour per gram. This is showing that we can have good reversibility up to 900 cycles. Still, this is far away from being applied as a battery material in technological applications, but we have worked closely together with a company in Germany, BASF, which is a large chemical corporation, and they have, started to interact with us on that field. The interesting part is, now from a scientific point of view, if you look at the performance of a high entropy oxide in this application, it has a good stability. But if you take any of the other transition elements out, for example, the cobalt or the copper or the zinc, you see that the material decays. So it seems that the high entropy is important to stabilize the cycling behavior. And we have some ideas on how that works, but let me try to briefly mention it. And we have studied that by detailed electron microscopy and X-ray studies. We do not incorporate all the cations in the electrochemical conversion of the material, but some of them are not participating in the electrochemical reaction, but they provide a stable rock salt structure in the entire process. And this way, the system has kind of a memory of that structure, and it will cycle back and forth between lithiated and delithiated structure. So this is what we have proposed, and other people have also confirmed that. Yeah. I go ahead and I show you that this has even resulted in a battery where we have combined a high entropy material as an anode and a regular commercial material NCM11 as a cathode. And you see here the performance in a small pouch cell type of a device. Yeah. I showed you that also other materials can be prepared. And here is an example of the fluoride structure, which is shown over here, rare earth type of systems. And they're interesting not only because they address different properties, in particular optical properties and band gap, but they also have a rich variety of different valencies the ions can have. But it also shows in this case that the 4+ ion cerium is very important to stabilize the structure. And this is just, again, showing the perfect crystallinity. It shows the single phase nature, and it also shows by this APT that we have a homogeneous cation distribution. It also shows if you take one element out, the cerium, that then the single phase nature disappears. And this is shown here. No cerium. We have secondary phases, which are shown here with the little stars here. If you do cerium in it, we can basically go with any of the compositions and we obtain the fluoride structure and single phase. Yeah. So the cerium here plays a very dominant role in the whole process. What we have also shown is that we can create a lot of vacancies in the system. And this can be measured by a Raman spectroscopy. Here is a pure cerium oxide, which doesn't have this particular Raman line here, which is indicative of vacancies. So if we add more and more cations to the system, we have more and more oxygen vacancies in the system, which is of course also important for the properties. We can also play around with the atmosphere of the material that we, or the atmosphere that we use to expose the material to, and we can change the band gap. And substantially, we can change the band gap, which is measured over here between 4 and 2.2 eV. So we can do that reversibly by changing the atmosphere between hydrogen and air. And this, of course, is interesting. And we could identify that this is due to intermediate band gap positions we can create by the different gaseous environment which we can have. So tunability of band gap can be an important and interesting aspect. You can follow that actually nicely also by the color of the material. Now I would like to show you how complex it can become by going to perovskites. In perovskites, we have now two positions for the cations, the A and the B position, and we have A site disordered, so that would be the rare earth for the different transition metals which we have. We can have B site for the different rare earth atoms, or we can go to even that structure. We have 5 rare earths and 5 transition metal cations in there, and still it behaved a single, or it became a single phase. 6 out of the 11 we prepared were single phase. And you can go to high resolution electron microscopy. You can identify the columns where the A atoms and where the B atoms are. And you see again, it's a single phase orthorhombic perovskite, which we have formed. And you can actually identify also where the different elements are located. Yeah? In a cooperation with Professor Hahn, who was recently also visiting here at Irvine, from Irvine, he was visiting us here in Oklahoma. We have done a very extensive study of the different perovskites which we have paired. So this would be a simple perovskite, and then we have 5 transition metal, then the 10 elements, and this would be another one material. And what they can do in using this advanced microscopy, they can look for the bond angle between the transition metal ions. And this is decisive also for the magnetic properties. So in this study, we could correlate this bond angle modification, which you can follow here. We can relate that to the magnetic property of the material. And this is, of course, very interesting because you can correlate something which happens between 3 ions in the system to the macroscopic property of the material. What we see is a broad distribution of these kind of bond angle, which is decisive for the properties which we have now looked into more detail, which goes beyond here the scope. So we could actually, even in this very complex compositional space, we could correlate properties to the atomic structure of the material. Now, the last few minutes I would like to spend with a new aspect which I haven't mentioned yet. If you look at the opportunities we have in playing around in a material system which can basically use a lot of the elements in our periodic table, it can result in all the different structures which I have presented, a few of them to you. We can play with a composition between equiatomic, so 5 elements at 20% each. But we can also put 15 of one and 25 on the other. So we have a huge, gigantic compositional space which we should explore in order to get the best composition. So one approach to do that would be to be predictive. If we had a theory which would predict the property which we would like to have, then we could do that. It's very complicated for such a complex material to do that. So another approach would be high throughput methods for the synthesis, but also for the structural characterization and for property measurement. And we have done that on a very simple, using a very simple robot, and which kind of, starts from metal salt solutions, and it prints different solvents of salts into little pockets like it is shown here. And then we anneal it afterwards, make a high temperature treatment, and we convert the salt, which is typically a nitrate, into an oxide. And because now in each of the pockets we can have a different composition, we can scan the compositional space rather quickly. But this also means we need the synthesize robot, we need the characterization robot for structure, but also for the property. And we have done that for measuring hundreds of different compositions in this rare earth high entropy oxide system. So we have done an automated synthesis, we have done automated X-ray, we have actually used artificial intelligence to analyze the data, and we have done a graphical representation. So here, each of the dots, and I don't want to go into detail how it is determined, but each of the dots corresponds to one particular composition, which I can read off this chart. So you see all the different compositions we have done. In the background, we also have a property which we can put there. This could be, for example, the band gap, or it could be the vacancy concentration in the material. In addition, we have information on the structure. So here, the round black dots would be single phase. This one would mean single phase of a different type, and these here would mean multiple phases. So we see in which corner of this phase diagram we have multiple phase, we have single phase of this type or that type. In addition, we can overlay a property. So we can, for example, put the oxygen vacancy concentration or the direct band gap. And we have kind of a library which has a lot of data involved in a simple graphical representation. And luckily, we could publish this recently in a nice journal in Advanced Materials. And I think this is the first time that a graphical representation has been done. So let me summarize here. High entropy oxides, opportunities and challenges. I have shown you for rock salt, high entropy oxides, but also for related materials that they have an application in electrochemical energy storage for electrodes and maybe even for electrolytes. I have shown you that fluoride type, they have tunable optical properties that we can change the band gap and we can incorporate a lot of vacancies. I have shown you that we can also correlate the exciting magnetic properties of such complex oxides with a local structure of the material determined by electron microscopy. We have done a lot of work continuing, which I did not present, also on the charge distribution and the local structure of these materials by using also advanced microscopy methods. And then the last thing was, to explore the vast compositional space by high throughput techniques, which I think could be a field of the future if you combine that with artificial intelligence and machine learning techniques. My conclusion and take-home message, if you are a material scientist, I think it's fun to play with defects and disorder. We always find new, advanced materials. So for me, my motto is I would like to continue this kind of approach for the next few years, that I can still contribute to that. Of course, I would like to thank a lot of people, because I didn't do the work myself, I typically come up with an idea, and then people take it and they bring in their own ideas. And this is just a small selection of the people who are still at INT, who have been at INT, working in this field. And of course, I'm trying to also work now with colleagues in here at OU to bring some of these ideas forward. And for example, with colleagues in CBME in the field of catalysis, because they have a lot of expertise which I don't have. And maybe we can use some of these approaches for that. With that, I would like to thank you for your attention, and I apologize for being 10 minutes, I think, over the time. Thank you for attending the lecture.
Wow. Yeah. Thank you very much, Professor Horst, for the very interesting presentation. It was quite exciting for me. Even though I'm not really conversant with materials so well, but one of the things that was quite interesting to know is that defect could be an advantage in what we could make out of it going forward. All right, so because of our time, I think I will just open the floor for discussions. I know we have some questions I would like to ask, or maybe some contributions, some comments we want to make on the presentation. So please feel free to unmute yourself and bring in your contribution. Thank you.
I mean, there's one question in the chat whether on slide 66 oxygen atoms are identified using experimental STEM. What we have done is we can measure the charge distribution, and actually at sub-angstrom resolution. So basically, you see the charge distribution in your material, positive and negative charges on the level of being smaller than the atomic size. And so that can be done. And so you see actually the different cores where the ions are located, but you also see the electron cloud between. And in this way, you can actually locate where also the oxygen atoms are located. Yeah. This is a very advanced technique which was developed at Irvine by Professor Zhaojing Pan, and we are collaborating with him. Yeah.
Okay, great. Thank you. My question is regarding that oxygen only, the question of oxygen identification.
Mm-hmm. I think other than that, you know, in the other high resolution work, you don't see the oxygen.
Yes.
Yeah. You typically see the transition metal and well separated from the rare earths in these perovskites, and you can distinguish between the different materials, and you see there are separate columns in the crystallographic structure where you only see rare earths, or you only see the transition metals. So that's possible, but the oxygen there is not detectable.
Yes, but in left side image, I think some oxygen sites is also visible in slide 66.
Let me go there. Yeah. Now, where is it? Here.
Here in the top.
Yeah,
top
that's
left.
exactly. This is this charge distribution. Yeah. And
yes.
so here you can see it. Yeah. Because of the charge. But in
okay.
Yeah.
Yes, here in the white, yes, white atoms that shows.
Yes,
in the
exactly. Yeah. But this is actually the charge. Yeah.
Okay.
Yeah.
And this in A side in top left. Yes, here white atoms are also oxygen atoms.
Yeah. Yeah, but I think it's I'm not sure. I would have to check on that with the experts. I'm sorry. But I'm not sure if this is really this is the position of the oxygen, yeah.
Yes.
But whether really we would identify it here, I'm not so sure. Yeah.
Okay. Great, thank
But I
you.
can find out, yeah.
Yes.
Yeah, thank you, Horst, for a very interesting presentation. I note that you are an experimentalist, and you have been brought here to establish a material science program. Perhaps I invite you to share with the folks out here as to what vision you have for a material science program that is anchored in the future, that goes beyond just experimentation.
Yeah, I mean, I think we have a lot of material science expertise on campus in different schools, you know, in AME, in CBME, in physics, in electrical engineering, and so on. But I think it's a bit distributed. And so the idea, which I was, you know, which Thomas explained to me, and you know, he has talked to others, and this also resulted in this discussions about COMET, that we would like to give it more visibility in itself, and to establish, you know, strategic areas where we have a strength at OU, and also show that to the outside where materials play a role. And this can, for example, also lead to increase the attractivity for students to come here if we can offer a PhD program which would you know, educate them in the broader field of material science, but still their degree would be in their home department. Yeah, so it's not a new department or a new school, but just give them the broad education in material science. Yeah, and I think that could be an attraction point for students to choose to come here to get their degree. Yeah. So I think that's kind of the idea, to strategically, you know, identify areas where OU has strengths, and also to establish a program, a PhD program, where we can, you know, attract students to come here. Yeah.
Thank you. Back to you, Andrew.
Yeah, all right. Thank you very much, Professor Horst, once again for taking out the time to give us this presentation, get us to know what's happening in this particular area. I believe Dr. Prakash would love to contact you privately later on for possible collaborations, because I see he has similar research interests. So I had well, my question is really not that technical, because I think some of the technical questions I had, you already addressed them in the presentation. Like when we're talking about high entropy materials, one of the questions that quickly popped up in my mind is stability concerns. But I think from your slides, you showed that that is well taken care of. But I'm thinking more in terms of market transition or adoption, if I will call it that. Because I know, like during my master's research, the study I did was on thermoelectricity. And most of the materials that were out there, they were very new materials, but it was still bismuth telluride that was really like the base material that you have in the commercial, you know, applications. I've left that research for a while. So my question is, what stage are we with these, you know, new materials like the nanoglass, like the HEM, is there the possibility that in the next few years, these materials will be available, readily available for those applications at reasonable price? Because I think the cost was also one of the big deals with those thermoelectric materials.
I mean, I will be very honest with you. I think in the field of these nano classes, I don't see much of a development towards an application. I think I consider that, at least for myself, as an academic exercise. And I think, I mean, I don't know if it's philosophical, but I mean, it's an academic exercise, because people have worked for 50, 60, 70 years on metallic classes, and they always did, I mean, I would say 90% they did rapid quenching. So by limiting yourself to one processing technique, you cannot expect that you find something different, okay? So people have done this compositional complexity, going from binary system, what Duvest did, gold, silicon, they went to 5, 6, 7 elements, and they got from a tiny piece, they go to a bulk piece, okay? And that has led to certain applications, okay? So for example, if you need the soft magnetic material, then you can make a metallic glass, okay? So you can find it occasionally in our surroundings, yeah? And the nano classes, I think it's an exercise that our views were so limited to this one processing technique that we didn't look left and right. And what this work has shown is there is a left and right, that there are other amorphous structures which you cannot reach if you do rapid quenching. And I think this is interesting from a basic science point of view. For myself, I gave up looking for application there. Quite in contrast, I would say, is the field of high entropy oxides, or high entropy materials in more general terms. And this has led to a tremendous interest in the last few years. I mean, the number of publications, the number of citations. I mean, even though I worked on nano classes 10 years longer, these papers are not cited as frequent like a 2 or 3 year old paper on high entropy materials. So the interest is much larger. And I think it has to do with 2 factors. One is that, anybody can produce this material. I mean, you can go and buy 5 different oxides in a bottle, okay? And you take a mortar and you grind it, and you take it at a furnace at 1,000 degrees, and you have a high entropy oxide at the end of the day. So this is one technique. There are 5, 6, 7 others which people can use. You can make thin films or powders or bulk. There is a lot of variety, and so everyone who has a lab can prepare it. So people jump at it because they can make it. The nano class, you need a very specific, very high, expensive equipment, okay? And so the number of people who can do it is very small, yeah? And here you address a large community which is ready to jump at it, and one guy has expertise in electrochemical, the other one in magnetic, the other one in optical, the other one in ferroelectrics, and they make the material and then they study it. So I think the response is much faster because of these 2 reasons in a way, yeah. And I think that is also something which you can take as a take-home message for selecting a subject. I mean, if you don't want the competition, you take something which only you can do, but then your feedback is small, okay? The response of the system is small. Or you try to find something where a lot of people can jump at, and you have to be always a step ahead in order to be the leader. Yeah, and so it's, it has its plus and minuses, but I think the fact that we have also an area where there's a lot of interest in the community in energy storage. This, and where we have shown that we can make contribution there, has led to a very fast growth. Yeah.
All right. Yeah, thank you very much for that explanation. So I think at this point we should be coasting home. I would invite one of our co-chairs that's still with us to give us closing remarks, and then Professor Farouk could also chime in as well, and then we can be done for today. Over to you, Rachel.
Thank you very much, Horst. My hope is that you would think broader than just material science. We've talked about that. Material science is, we have to distinguish as to what makes Oklahoma the leader, not just having the same program that other people have. And so I'm interested in seeing how you would come along and say how Oklahoma becomes a leader that others will follow, as opposed to being just one more group that people can come along and say, oh yeah, they're going to do some material science. That's where I come from. And if there's, if you're interested, we can continue that conversation.
So we stay in contact, Farouk, okay? So
I'm sorry?
I need help and advice as well, yeah.
Okay. So on behalf of the graduate student community at the Gallagher College of Engineering, I'm really grateful for your talk, for having volunteered to give it, and I'm very grateful to Andrew for having moderated it. And we will have a link to the recording, which we will circulate and put it up on our YouTube channel. So thank you all very, very much, and we look forward to a continued dialogue.
Okay, thanks a lot, and okay, bye-bye.
I'm going to stop recording. I'm going to stop recording.